right. So light with this 400 nanometer wavelength. What color is this?
Purple. Violet.
Yeah, violet, purple, whatever. Violet, awesome. That is violet color. Is incident on a metal surface. Electrons are ejected with a maximum kinetic energy of this. All right. If I give you the wavelength and I give you the KE, what should you be able to find right away, Michelle? Do you have your phone with you now?
I left it at home.
Helen's. What equation are we using on this problem? What is this problem? Right. Do you have it in front of you?
Yes.
Okay. So, what part of the photoelectric effect is not here? Yeah, work function. You see, like, without even looking at this, like, I look at this and I go, oh, look, I could find the work function if I wanted to. Because I have the KE and I have the lambda, which I can convert into E, right? Okay, all right, anyways, move on. Calculate the frequency of the incoming light. Frequency of the incoming light. That should be, wow, I say that's a no-brainer. It's going to insult somebody. Van, what equation do I use for A?
Out of the box.
You've got to think outside the box for this one. Do what? I heard V equals, right?
She said V equals lambda times frequency.
Oh, okay, cool. V equals F lambda. Okay, I'm not mocking you, I just couldn't hear. Sorry about that. So Van gives us the exact right equation here. So then we just say F is C over lambda, right? Everybody cool with that? Good. Then calculate the work function. Boom, boom, boom. And then Helen got us here already, right? She said KE is equal to HF minus phi. Okay, so phi is equal to KE minus HF. And we conveniently just got F in part A.
No, HF minus KE.
Yeah, HF, because negative I.
Oh yeah, I knew that. Very good. Excellent. Oh, you caught that. Excellent. I was testing you.
Yes.
It was a test. Everything is a test. All right. Calculate.
You can start studying now.
What's that?
You can start studying now.
I know, right? Then calculate the stopping potential for the emitted electrons. Okay. Do you remember the? Actually, let's just do this because this will make this very. That's pretty funny, actually. Okay.
Is that being recorded as well?
Yes.
That's awesome.
Okay. Yes. Excellent. It's funny. I used to do that all the time in volleyball. You stand in front of the net and then pull the net, like pop it down, and then go with the net like this. So when the people on the other side look, they're like, it looks like the room is bouncing. All right. Anyways, how convenient. This is already set to 400 nanometers, right? So how do you turn this on?
That's so important.
Switch.
Flip the switch. What's this? Oh yeah. Okay, so that's intensity. So we're shooting our beam of purple light at this. And do you see what's happening? Yeah, what are those things? Electrons. So if I'm shooting a beam down and electrons are moving from one place to another, why are the electrons moving? Yeah, energy. What type of energy did they get? Kinetic. Energy of motion. That's why electrons are moving. Okay. Now, how do we normally get electrons moving? What's that? I guess so. How do you normally get electrons moving? Yeah, at a voltage, right? At a battery, right? In your cell phone, you put a battery in, electrons move, everything works. So the battery puts an EMF that gets electrons moving. Does that make sense?
Yeah.
So there is, the battery adds a voltage. There is something called a stopping voltage, which, I don't know, it's just sort of a measurement of how many volts that photoelectric effect thing is doing. So if I take this and I put the voltage to a certain level, right, I can get the electrons to just like they should just, the maximum ones should just get here. But I can basically get the current to 0. And this is called the stopping voltage. And that voltage is a function of the energy of the electrons. So if we take a look, okay, wait, this isn't right. Okay, that was weird. I thought I already chose to. This is seriously the stupidest thing that Apple computer has ever done. Okay, so let's just check here. V is F lambda, boom, we did that correctly, so that's good. Here, K HF minus phi, phi is HF minus K, boom, we did that good. And here we go. Okay, the stopping voltage is simply a function of the energy equals energy. Now, how do you get energy from voltage? Right, because voltage is equal to what per what? Joule per Coulomb. So if you want to know the energy from, or the energy in certain electrons, you just multiply the voltage times the charge. If you multiply the voltage times the charge, then boom, get what you're looking for. And then, of course, how do we know that this is an electron? Because it said the light is incident and it releases electrons. So that's it. And then this is the stopping potential or stopping voltage. And remember, keep that sort of mental picture in your mind. A stopping voltage is the amount of electric potential that matches the kinetic energy of the particles so that they will never be able to come up and touch and cross the circle. So it kind of like shuts down. So it's going to like put enough energy back the other way to prevent the electrons from coming out. Alrighty. Okay, and then calculate the momentum of an electron with the maximum kinetic energy. Okay, so this is just algebra right here. Right, because kinetic energy, oh, that's weird. I don't normally write like that. Kinetic energy is 1/2 mv squared, right? Well, how do I make this into momentum? It's 1/2 p squared over m. Does that make sense? Do you see that? Because p squared is m squared v squared. So p squared over m is mv squared. And then p squared over 2m is 1/2 mv squared, which is equal to kinetic energy. So 1/2 p squared over m is that. So now I can just solve this and say p is equal to the square root of 2ke over m. Where do we get the ke? Why is it over? Did I do that in algebra wrong? I just moved this over here. Oh, that's on top, so I should have done it with that. Thank you. Should have been m there. Thank you. So yeah, I gotta move all that up to the top. Do correct algebra and everything works. Yes. Only if you can tell me the photoelectric effect equation without looking down. Oh yeah, that's right. See how bad she has to go now.